There we go. Section 5.7 starts off giving you these theorems, right? These two sort of points of interest about the natural logarithm function. So it says, let u be a differentiable function of x, right? And that's just because we've been doing u substitution since section 5.5. If you don't have sort of a more complicated function, you just have 1 over x, then the integral of that with respect to dx is the natural log of the absolute value of x plus your constant of integration. And that should be pretty natural if you remember from Calculus 1 that the derivative of the natural log function is 1 over x. So if you think about this like a little differential equation and you wanted to cancel out the derivative, you could take the integral of both sides. And then so we would get the integral of 1 over x dx equals the natural log, right? Since we're kind of going backwards. Octavio, can you see this all right? Do I need to zoom in? Try to make it a little more full screen. Let me get rid of this little notification. All right. So let's do some examples just to see how we can put these into play, because a lot of times, your calculus instructors will say, here's a theorem, apply it, right? But seeing is believing, and we want to actually see how that works in practice. So the first example from the textbook says we want to just integrate, find the indefinite integral of 2 over x dx. And I'll zoom in for this. Okay. Now, that takes the form of this first part of the theorem, 1 over x dx, because we can just pull that 2 out as a constant, right? So we can pull that out of the integral. I'm just going to do that over here. 2 times the integral of 1 over x dx. And so the rule, the theorem above just says for this part here, we can now simply take that integral and we'll have 2 times the natural log of the absolute value of x plus c. Okay. That's it. Really easy application of that process, provided that we can process what we're looking at here and sort of pull out that constant and everything kind of looks normal. Now, there is one note here, and that is a throwback to college algebra. So if you have a log, you have this property of logs called the power property, where if you have, let's say, log base b of x to the n power, then you can rewrite that as taking the n here, moving it to the front of the log, and writing that as n times log base b of x. Okay. So that's just a property from college algebra that maybe, we haven't seen in a while, and that's okay. That's why I'm bringing it back up. But that applies for natural logs as well. So like if you have, for example, this answer that we got, which was 2 times the natural log of x, right? We had that expression. Then if you wanted to, it would be equivalent, okay, to take this 2 and kind of reverse this process where you put it back on the x as the exponent. Okay, so that could be rewritten as simply the natural log of x squared inside the logarithm. So this could be rewritten as natural log of absolute value of x squared plus c. Just make sure that the square is on the x and not on the outside, because sometimes it becomes ambiguous whether the x is on the inside of a set of parentheses. Sorry, whether the exponent's on the inside of the parentheses or whether it's on the outside. And that was something that I was noticing as I was going through some of these examples, not only from the textbook, but from the homework. Because, I just really think that if you're going to give students a problem in math, you want to make sure that the notation is clear, right, where that exponent lies. And sometimes with certain functions like the log function, we don't put a parentheses around the x, Or like with the sine function, sometimes we just put sine x and we don't put the parentheses to indicate that this is a function and the x is going inside. So then it becomes kind of like confusing if the x is squared or if it's the x is squared on the inside or whether it's like sine squared x. Okay. So as we sort of go through problems like that, where that becomes ambiguous, I'll try to clarify so it's not so daunting. Okay. But that was like the really easy sort of to be not too disparaging, but like the baby level application of this theorem. Okay. Then it's going to ramp up a little bit, and we'll have to apply things that we learned from previous sections, like U substitution. So, for instance, for this next example, if we're taking the integral of 1 over 4x minus 1 dx, okay, we can kind of see that it takes the form of some like 1 over something, and that something is a function of x, right? So here would be a really nice place to go ahead and just say, let's use U substitution from section 5.5, right? And we'll call this thing on the bottom U for x minus 1, okay? So then going through that sort of procedure that we did for U substitution, we will go ahead and take the derivative of this, which is just going to be du is equal to, well, that's just going to be 4. That's going to turn into 0, and then we'll put dx. Okay. And so du is equal to 4 dx, which if we remind ourselves we want to replace the dx here in the problem, then we need to get dx by itself in this little equation that we've made up. So how do I move the 4 over to the other side? Divided by 4. Okay. So we know to divide this by 4, but you're going to start seeing me do this thing where I say, okay, if we're dividing by 4, this is just going to be 1/4 du. Are you guys okay with that? Equals dx. So when we make that substitution, you're also going to see me get a little bit, bless you, see me get a little bit lazy, where I'm going to say, okay, so this is a constant 1/4. I'm just going to pull it out of the integral. Okay, so I'm going to put the 1/4 in the front of the integral just to kind of cut down on writing. So there goes our 1/4. We have 1 over this thing on the bottom is what we're calling u. And then we already have our 1/4, so we just need to put the du in here. Are you guys okay with that, or is that kind of too fast? Okay. So again, like sometimes doing things in your head cuts down how much writing you're having to do. And I know with these calculus problems, if you're trying to work them out, it's a lot of rewriting and trying to figure out like, okay, how do I need to put this? What form is going to be easiest for me to see the pattern, right? So I can apply the pattern. But now that we have this, we can just use that integration rule that we have, which is 1/4. The integral of 1 over u du is just going to be the natural log of the absolute value of u plus c. Okay. And then we want to go ahead and go back to the world of our original variable x. So that's 1 over 4 times the natural log of the absolute value of u, and u was equal to this 4x minus 1 plus c. And that's it. We'll call it a day. Any questions about those two examples? Comments? All right, let's see. I think I wanted to do a couple examples from problem number 4. Okay, let's get a new sheet of paper. Let me go ahead and grab some more paper over here. Put you, oh, you're in here. Let me just, okay. This is example 4 from the book, but I'm just going to write it as number 3. Okay, and that is going to be 4. I say I want to do 4a, b, And that is secant squared over tangent x dx. Okay. So it's kind of the return of our trig functions. Okay. Okay. So we're going to start seeing some trig functions in this section. So we just need to remember just a few things. One, what we're trying to do here is write this integral as 1 over x or 1 over u, right? So if we think about this for a moment, the denominator is what we want to become u, right? So for our trig functions, we then have to say if u is equal to tangent x, do you guys remember what the derivative of tangent x is? It's secant squared. Yeah, for sure. Right. And that's exactly what we wanted, because this integral could be rewritten, and if you needed to do this, you can 1 over tangent x times secant squared x, where we're just putting that on the side, dx, right? And maybe that's a sort of family friendly way to write this because like once we take the derivative of tangent x, we'll have secant squared x here, dx, and that's the exact thing that we're trying to replace in our problem, right? So this is going to be du, this denominator gets turned to u, and so we can write it in the form where we can just apply that natural logarithm integral rule for us. So that's 1 over u. This whole thing is du. And based on the rule, that should just be the natural log of the absolute value of u, which happened to be tangent x based on our definition. Okay. Plus c, and then we can call it a day. Yeah.
So like, is it preferred like if something like is like the numerator is preferred to like take it out, so I could be like 1 over like whatever it is.
Yeah, I think like that's always a good strategy to sort of split up this fraction, right, as 1 over the denominator times the thing that's on top,
Oh.
right? That's always going to be like a good strategy. Not for every single problem, because as things get more complicated, that might not always work,
Yeah.
but it's a good place to start. Yeah. Okay. Let's go ahead and look at another one. I think I wanted to do D. Okay, so this is going to be our fourth example, which is example 4D in the textbook if you wanted to look at it yourself. That integral that they're asking us to find is 1 over 3x plus 2 dx, back to our normal kind of rational function with a nice polynomial on the bottom. So again, if you're having heart palpitations whenever you see trig functions, we kind of need to get over that anxiety and sort of practice that. But for now, we get a little bit of relief. All right. So what am I going to call u in this problem so I can start integrating? Any ideas?
3x. So
Yeah, 3x plus 2, right? Not a secret, right? That we're looking to sort of change that denominator to a u. So u is equal to 3x plus 2. And then if we take the derivative of that, du is going to be equal to 3. And then that constant disappears. So that's just going to be 3 dx. You guys okay with that? Okay. Now, we don't have a 3 dx in this problem, right? We just have a dx. So what do I need to do with this 3? Divide it over to the other side. And again, I'm going to start getting lazy with this. I'm just going to say I'm going to multiply 1/3 on both sides. And that's how I'm going to get dx by itself. Okay. So now I can make that replacement and rewrite my integral. So I'm going to have 1/3 pulling out of the integral since it's just a constant. I'll have 1 over u, and then the dx can now just be the du. right? And there she goes. That's going to be 1/3 natural log of the absolute value of u. And again, if you want to cut down on writing, you don't have to write the absolute value of u. You can just go ahead and make that replacement and put the 3x plus 2 back in there. And then don't forget your constant of integration. Also, one thing I was noticing, I'm sure that you guys are going through the homework at, the pace that makes sense for your life, for your schedule. I am also going through the homework problems just to make sure that there's not any sort of tricky problems that we need to like draw attention to. Um, and I noticed that, and maybe you guys have seen this, if you put a lowercase c in WebAssign, it won't accept the integral. So just make sure that you always put a capital C here. Okay. So maybe I'll just make that note in WebAssign. Always use capital C. Okay. Um, from a mathematician's point of view, like capital lowercase doesn't matter. You could call that Q if you wanted to, as long as you identify that Q as a constant, it doesn't really matter what you call it. Okay, but WebAssign's being very picky there, so um, just watch out for that. Questions, comments about that one? Feel okay? Okay, I'm good. Let's see what we got going now. All right, now the rubber meets the road. Do you guys remember polynomial long division? Of course. Of course we don't, right? It's been a long time since, I don't know, you guys did it in uh maybe you did it in Math 1414 in college algebra. So that was Cal 1, Cal 2. That was like a year ago or more, possibly. Okay. I'll stop rambling. Let's jump into this problem and I'll show you like where polynomial long division is going to have to be a tool in our toolkit. So we're going to take the integral of x squared plus x plus 1 all over x squared plus 1. I'm going to zoom in again. Give you guys a moment to write that down. Okay. So in the previous problem, and maybe I want to write this in pencil, I don't know. What we were trying to do is like take the denominator and call that u, and then its derivative would end up being the numerator, right? And if we had that, then we could go ahead and use the natural log rule here. But if you take the derivative of this denominator, it's not going to be, its derivative is not going to be this numerator, right? Because they're both in terms of x squared. So if you have a polynomial divided by another polynomial, then we want to go ahead and apply long division. Long division, if you vaguely recall, will look something like this. We're going to put the thing on top, x squared plus x plus 1, underneath this little division symbol. And then we'll take the denominator, and that goes on the outside. I'm going to put x squared plus 1 here. You don't have to put parentheses. I'm just doing that for, I guess, comedic effect, if nothing else. Okay. Um, But then we need to figure out like how many times does this factor go into this polynomial, right? And maybe that's a weird thing to ask. So instead, we kind of simplify it. I always do my scratch work down here. So I'm just going to put this is scratch work. What we're going to do is ask ourselves for this term here, x squared, how many times does this x squared go in there? So I'm going to say x squared divided by x squared. Okay. And what is x squared divided by x squared? Yeah, that's just 1. Okay. So if that's what I got as my result, I'm going to put that in on top of this division symbol. But notice that these terms are kind of going in order of descending exponent, right? Exponents go from biggest to smallest. If this is just a constant, I'm going to put it right above my constant column. Okay. So once I have that, Just like regular long division, you're just going to take the 1 and multiply it by both of these things. We're going to put that result underneath here. So I'm going to put 1 times x squared is x squared. Again, lining up my terms with their exponents, right? 1 times 1 would just be 1, which is right here. Okay. But we kind of have this gap here. So if you'd like, you can put a 0 there. Now, with regular long division, you subtract this thing that you multiply. Okay. So that means we're going to have x squared minus x squared. These cancel out. Okay. We're going to have x minus 0, but that's just going to be x. And then we're going to have 1 minus 1. So if you want, you can change the signs here if it makes it a little bit clearer to you. And that's just going to be 0, so we can just cross those out. Okay. Not the greatest example in the world. Whenever you're done with this long division process, your result should look something like this. We have 1, which is the answer on top, right? Plus, it's always going to be the remainder over the original denominator, which was x squared plus 1. Okay. So in math speak, usually we call this the quotient plus the remainder over the original divisor. Okay, that's the form that we're looking for. Okay.
Um,
Yeah.
That one came from just the X squared over X squared.
Yeah, exactly. So when we did the x squared over x squared, we got this 1. So this guy up here, whatever is up on top, that's going to be your quotient. Okay. This down here is your remainder. And then this guy here was your divisor. And we're going to do another example because this is kind of like a weird looking long division problem. And maybe before we do the next problem where we involves long division, maybe I'll just review what long division looks like with numbers because I think like after you get out of grade school, you stop doing long division and you're just doing it in the calculator, right? So you kind of forget that whole process. But let's go ahead and proceed. Now that we have this result, what that means is that this whole expression here that we were trying to take the integral of, sorry, and I didn't even put the dx, shame on me. This whole thing is going to get replaced by this new expression. Okay. So we're going to take the integral of 1 plus x over x squared plus 1 dx. And sometimes you'll see in the textbook, they'll put a parentheses here. Just because now we have 2 terms, we're going to have to integrate each of them separately. Okay. So let's just, for clarity's sake, I'll rewrite that as the integral of 1 dx plus the integral of x over x squared plus 1 dx. So there's 2 integrals that we have to do. Luckily, the first integral is just a 1, right? So when we integrate this one, we should just be getting x. Okay. And then this guy, even though maybe it doesn't look any more simplified, now if I took the derivative of this denominator, right, then I could get the derivative in terms of x. So now we can apply u substitution. So we'll go from there and use u substitution. So we'll call this, the denominator u is equal to x squared plus 1. Du is equal to 2x dx. And we really want to replace this x dx, right? Right, this x dx wants to be replaced. It wants it so badly, right? But we have a 2x dx. So we just need to divide the 2 over to the other side. Okay. So if we do that, we'll get 1/2 du is equal to x dx. And we can replace that x dx in the problem now, right? So this is just going to be plus the integral of, and we're pulling out a 1/2 here. So I'm going to squeeze that 1/2 in front of my integral sign. 1 over u, and then the x dx gets turned to the du now. Kind of some acrobatics going on there, right? I think that's all we need for this problem because now we can finish it up, right? So we have this part here where we have x already done. Don't have to worry about them, just dragging it down. Then we have plus 1/2, and this guy is just going to be the natural log of the absolute value of u plus c. And I'm just going to go ahead and plug u back in, which was the x squared plus 1. I'm going to wrap it up because that was kind of a doozy, and we don't want to sort of do any additional processing there. Any questions, comments? Zoom out just so we can see the full scope of what we've done here. Like I said, once you get to a certain point in calculus, and I think we're getting there now, sometimes you're going to have to do a lot of scratch work on the side in order to sort of process these problems. But like if I set the scratch work aside, there aren't that many steps here, you know? And this is me just trying to comfort you. I know I'm not doing a good job of doing it, but like we got to practice this polynomial long division if we become unfamiliar with it, right? Because it's going to be a really useful tool. So that being said, let me go ahead and pull out one of the problems from the homework that involve polynomial long division. Okay. One more note here. In the textbook, it says if you look at just this part here, the natural log of the absolute value of x squared plus 1. Do you guys know why we're using absolute value here? And no is an acceptable answer. Okay. The reason why the absolute value is here is because in the world of logarithms, at least until you get to an upper level math class, the input of all logs, including the natural log, has to be positive. Do you guys have your calculators on you right now? Go ahead and pull out your calculator if you have it. And I'll show you guys on the screen. Like, I'm just going to grab my calculator, clear a bunch of this stuff. I'm going to zoom in. If I type the natural log and give me a negative number, just any negative number, -2, I get an error. It says unreal answer, right? Non-real answer. So there is a higher level of mathematics where you can put negatives into logarithms, but for now, what we are going to say is that the domain of logarithms, the domain of the natural log, has to be greater than 0. So even if I try to put the natural log of 0 here, I'm getting a domain error, right? It's only as soon as I get to 1 that it stops giving me an error, right? And you can also put the natural log of a fraction. You could put like 1 over 2, and that doesn't cause any errors, okay? So we're using the absolute value here, and it's necessary, and you guys can't see what I'm writing. Let's see. Necessary because the domain of the natural log function, x has to be greater than 0, and that's just a fancy way of writing x has to be positive and not 0, okay? So I remember, I'm starting to get flashbacks as I go through this text to my Calculus 2 experience and just wondering like, oh man, why am I getting points off for not putting the absolute value bars? It's very easy to forget, but you really want to, drill in your head those absolute value bars need to go first, and then we'll replace the u at the end. Okay. All right, let's do another example so we can see some more polynomial long division. I know you guys are dying for it. Okay. So this is a homework example. That was kind of a normal long division. That was kind of a normal long division. Okay, we'll do this one. That's fine. We're going to take the integral of 2x squared plus 9x minus 1 all over x minus 1 dx. Zoom in. Give you guys a moment to write that down. Sort of give myself enough room to do my scratch work here. Are you ready? Ready as you'll ever be. Okay. So, actually, before we jump in, sorry for taking all these little breaks. Let's think about regular long division. Again, this is not a review from even algebra. This is going to be a review from like, I don't know, elementary school, okay? But I'm not trying to insult anybody here. Sometimes it's nice to go through the basics, just to remind ourselves how that works. So like, let's do something like, man, I'm going to try not to make this divisible by 7, but we're going to do something divided by 7. Let's go with 158 and let's pray to God that it's not divisible by 7. Okay. When you're doing long division back in grade school, right, this would be equivalent to 7 over 158, just to write it in fraction form. What you're asking yourself, is how many times can 7 go into each of these place values? So we said, like, how many times can 7 go into 1, right? And it can't. It's like too big. So sometimes we leave a blank there. I never liked leaving a blank, so I say it goes in 0 times, right? Because 7 is too big to go into a 1, right? Evenly. And then you could say to yourself, well, 0 times 7 is 0, right? So you would put the 0 here and subtract it. The zeros we usually skip, right? And just move on to the next thing, but I'm just showing it for convenience sake. And then we do the subtraction, and whatever comes down, we bring it down. So like 1 minus 0 is going to be 1, and then we drop the next place value here, 15. Yeah.
We made a 158 over 7. We put 7 off.
Yeah, you're absolutely right. Good call. 158 over 7. Sometimes when I'm talking and I'm writing, I can't think straight, right? I'm going to make those mistakes. But one little thing that I teach, like whenever I'm doing things below college algebra with students, I always tell them that the numerator is the cowboy and the denominator is the horse. The cowboy sleeps inside the house. The horse sleeps outside the house. I know it's silly, but it kind of helps people remember. Okay. But thanks for that catch. Okay. Good. But back to this thing, right? 0 times 7 was 0. We did the subtraction. We brought down what was left over. We still have 15. And then we just ask again, can 7 go into 15? And if so, how many times, right? So we'd say it goes in twice. Then we do a multiplication, right? So we do 2 times this thing on the side, and then we put that number here. And then we subtract it, right? Go ahead and subtract it. 1 minus 1 cancels out. 5 minus 4 is just a 1. And then we bring down the next place value, that next digit, and we have 18, right? And then we do the process again. How many times can 7 go into 18? That's going to be twice again. Okay. And 7 times 2 is going to be 14. I'll put a 14 here. Then subtract it. Then find the remainder, right? So that's just going to be 4. And now, you guys are mature enough in mathematics and I guess in life that you know we could just put a point here and then put as many zeros as we wanted to continue this process. But like back in grade school, we didn't do that. Back in when we were in elementary, we said, okay, this is the quotient. This is my answer, 22. 7 goes into this number 22 times evenly. Then we would say plus a remainder of 4. So sometimes you would write R4, right, when you were in grade school. I don't know if you guys ever remember that. It might be too long ago since elementary school. I vaguely remember this, but we're not going to write it that way. Instead, we're going to write it as 22 plus the remainder over the original divisor. So if you wanted to write it as a mixed number, you would just say, oh, this is 22 and 4 over 7, right? 22 and 4 sevenths. And that's essentially what we're doing with these polynomials. And you'll see in this next problem, like that's exactly the same format. Okay. I just do a little bit of extra scratch work because with numbers, we can do that multiplication in our head. But with polynomials, we need to write some of that stuff down so the thing isn't just in our head because that's where mistakes happen, right? So again, not to patronize anybody, long division is a fun process with just numbers, but like we're in calculus, so let's see how this goes. Let's do the long division, right? Cowboy sleeps inside. So we have this big polynomial, right? So we have 2x squared plus 9x minus 1. And we're going to do long division. Go ahead and bring that down. Cowboy sleeps inside. Always make sure that your polynomial is in standard form, that the exponents are going down in value, 2, 1, and then no exponents. And then we can put the horse on the outside, x minus 1. Okay. Rather than using the entire polynomial on the outside, that divisor, we're just going to focus on the x and ask ourselves, how many times can x go into this? And that's kind of weird to ask with polynomials. That's why I always put this scratch work down here. Because we're just doing, what is this 2x squared divided by x? How many times does x go into this, right? And if we just do that division, we'll get 2x. Are you guys okay with that? Okay. So 2x needs to go on top of this little fraction division house thing, right? So I'm going to put that 2x here in my x column. And then I'm going to take this number here and multiply it by this polynomial on the outside and write my answer down here. So 2x times x is 2x squared. Look at that. They match, right? And then 2x times negative 1 is going to be negative 2x. So we'll put that down. Okay. Then just like with regular long division, we're going to subtract these, which means their signs are going to change. So this is going to become negative. This one's going to become positive. Okay. So the 2x squared and the negative 2x squared, those are going to cancel out. You can cross them out if you'd like. And then since that sign changed over here with this negative 2x and became positive, we'll just add 9 plus 2 is going to be 11x. So I'll put 11x down here as my result. And then we just go to the next term and drop that down, minus 1. Okay. We're going to take a look at this 11x now and ask ourselves, how many times does x go into that, right? In other words, what is 11x divided by x? That should just be 11, right? So that now is going to go up here. So it's a positive 11, so be careful. Since that's positive, we're going to put a plus 11. And then we can go ahead and multiply that 11 and distribute it to this polynomial over here. So that's going to be 11x. And then 11 times negative 1 is going to be minus 11 there. And just like regular long division, we're going to subtract this polynomial, which means the signs are going to change. This will be a negative 11x now, plus 11, like so. And we can go ahead and combine like terms. So these cancel out. And we're left with negative 1 plus 11, which is just a positive 10. Right? Just to get a vibe check. Do you guys think that looks like regular long division? Yeah. kind of. So I always think it's really nice to go through this process to show that long division because with polynomials, it's pretty much the same mechanics. Okay. So since we're done with this long division process here, that means that our answer or this new expression that we're going to get is going to be written in the form 2x plus 11 because that's our quotient or q plus the remainder over the divisor, and our remainder was 10 over the divisor was x minus 1. Okay, so we're going to integrate this thing now. So integrate 2x plus 11 plus 10 over x minus 1 dx. And I'm going to put this in parentheses just so that we know we're taking the integral of each of these terms separately. Okay. So we'll integrate 2x dx plus the integral of 11 dx plus the integral of 10 over x minus 1 dx. Okay. This guy here will just end up being 2, and then the integral will be x squared over 2. So the 2 and the denominator cancel out. You guys okay with that? So that's just going to be x squared. Plus, this is just going to be 11x. And there's nothing interesting happening there. It's just going to stay 11x for our answer. Plus, now we can go ahead and take care of our final integral here. I know it's going to be 10 times something, but if I pull the 10 out and call this 1 over x minus 1 dx, then isn't that in the form 1 over u? Right? And that's what this whole section is about, using that natural log property, right? That natural log rule for integration. So if you're starting to get accustomed to this, and you can call this 1 over u, you could do the scratch work, and I'll do it over here. U is equal to 1 over, sorry, not 1 over. U is just equal to x minus 1. Then we can say du is equal to, well, that's just going to be 1 dx, right? So essentially du is equal to dx. You can call this 10 times the integral of 1 over u du. And that is just going to be 10 times the natural log of the absolute value of u plus c. So to wrap it all up, we have x squared, and you guys can't see what I'm writing. There we go, x squared plus 11x plus 10 times the natural log of the absolute value of x minus 1, close the absolute value, plus c. Okay. I spend so much time teaching college algebra that with those students at like really a beginner level, I'm constantly have to reassure them that these problems are a marathon. It's not a sprint. You don't run those races the same way. And so you need to make sure that you're taking breaks because like this is a lot of processing that you're having to do. And like even though you guys are, the big dogs in calculus too, right? Sometimes going back to the fundamentals, going back to the basics is really helpful. And maybe we find enjoyment in the process, but we got to practice this long division stuff because it's going to be really useful and it'll simplify the process because like the natural log rule that we've learned in the first couple of examples was pretty straightforward. And some of the u substitution we've been doing has also been pretty straightforward at this point with a little bit of practice. Maybe it feels even good or feels easy. Okay. But putting it all together, if you're doing the homework like, and there are only like 12 to 15 questions per homework assignment, if you're sitting there for 3 hours, like trying to knock it all out in one go, you're going to get exhausted, right? You got to build the stamina. And just like going to the gym, like you can't go to the gym for 5 hours and think that you're going to get like ultimate gains, right? You're just going to end up injuring yourself and you're not going to go back to the gym for several months, okay? So like make sure that you're spacing out your homework so that, you do a little bit in bite-sized chunks every single day. Maybe you say, okay, if I only have a couple of days to do homework, there's 15 problems, maybe I'm going to try for five a day, right? 5 problems a day, just to knock it out little by little, right? Yeah, because these are long. So that's my recommendation, kind of some analogies from life, and I think it's useful to think of it that way. Do you guys have any questions so I can get a little break from talking? Yeah, what's up?
So when you're dividing on rhythm, right?
Yeah.
You stop as soon as there's like no more X's.
Yeah, as long as I run out of terms, like I brought that last term down, and then that's going to be my remainder when I have no more terms to bring down. Yeah, good question. Any other questions? Take a little break here, right? How are we feeling? Example number 7. Let's see what this is gonna do to us. Yeah. Okay. Example number 7 is integrate 1 over x ln x dx. Okay. Now, I think Ryan asked this question earlier, like if I have, something on the numerator, can I just split that off and put it next to the dx? And usually that's going to be really useful. Um, but another thing that's really useful to know, and this is like a basic arithmetic fact, like if I have 1 over a times c, right, whatever those a and c are, then that's the same thing as 1 over a times 1 over c. I don't know why I didn't do a and b. A and c just jumped out at me, right? Just in terms of picking random variables there. Okay. So all I'm saying is that if I have 1 over something times something else, it might be useful to split that up into 2 separate fractions. Okay. So what we can do is say, here we go, let's call this, and I'm going to rearrange it too. I'm going to first say this is 1 over the natural log of x times 1 over x. Okay. You guys okay with that? Now you could put the 1 over x in front. It doesn't make a difference when you're multiplying things. The order doesn't matter. Dx. Okay. But we want to do kind of a u substitution here. And so we have to kind of remember like what's the derivative of is like the derivative of one of these things, one of these other things in the problem. And I'm not sure if I wrote it on the first page of our notes, but I did. And I'll rewrite it here. Recall from Cal 1, the derivative rule. The derivative of the natural log of x is 1 over x, right? And I'll rewrite it here. So d dx, the natural log of x, is equal to 1 over x, okay? And what that means is that this guy is du, right? Well, this guy in the dx is the du, right? If you can see it. But if you can't see it, then what we're going to do here is we're going to call we're going to call ln of x the u. So let u be ln of x. And then from our calculus review, the derivative of the natural log of x is 1 over x dx. And so now this whole thing over here can become du. Okay. So we're going to get the integral of 1 over u du, and that should give us, what should it give us? Just the natural log of the absolute value of u plus c, and u is the natural log of x, right? Just plugging that u in, okay? And that's it. Kind of weird that we have a natural log inside of a natural log, but that's what the rules kind of prescribe for us, right? So you kind of have to just learn how to trust the process. We have our u substitution, we plug the u back in, and doesn't matter what that u was, how complicated it was, it goes back in, okay? Now, there might be some trickiness here when it comes to WebAssign, and that is you just need to remember that the x needs to be greater than 0 for, and I'll answer your question here in a second, Mark, but just remember that the x inside of your logarithms needs to be greater than 0. So sometimes WebAssign is going to get a little bit tricky on you, and they'll throw another absolute value here around the x. Because we want to make sure that whatever this x is inside of the internal the internal natural logarithm is positive. And we also want to make sure that whatever this natural logarithm ends up being, that is also positive. Okay. A little bit tricky, but you might have to watch out for that. So let me see. We have a question in the chat. Could we use the power property here? Mark, what do you mean by the power property here?
Sorry, in the original question, it was 1 over x ln x, or natural log x. Could we have turned it into 2x, or am I misunderstanding the power property?
Yeah, we have a little bit of a misunderstanding for that power property. So let me go ahead and take a little time to sort of clarify that, right? The original problem was 1 over x natural log of x. So Mark is asking, can we do this? Where we write this as 1 over the ln of x. But remember, that power property says that this thing being multiplied in front becomes the power of x, right? So that means that we would have x to the power x, and we don't have an integration rule when we have x to the power x. When you start stacking variables, sometimes in higher level mathematics, they call those power towers, but they become like really complicated. So just be careful, because like if that were 2, then you would be correct. It would be ln of x squared. Yeah, you could do that. But if we have a variable here, we don't want to pull that inside of this other function, because then that input x to the power x becomes kind of unwieldy. Okay. So let's not do this. Okay. Unless you wanted to challenge yourself and see where it leads you, just in the interest of time, I don't want to go into it that matter. But if it were a number, then we could do it. But if it's a variable, we don't want to pull it in to make of the variable an exponent of the variable. Okay. Good question, though. And you guys can't see this, but you turn off these notifications. Let's not do that. Okay. All right. Derivative rules for trig functions. This is me just reminding you what the derivative rules for trig functions are. So I'm going to leave it on the screen for a second. I wouldn't recommend writing them down, because like on that handout I gave you guys, I think in the beginning of the semester, or like the second day of class, I gave you a printout of the derivative rules, the basic derivative rules, basic integration rules, and they're all there. For those of you that are in Zoom, that are taking this class remotely, if you just do a quick Google search of the derivative rules for trig functions, you'll get this, right? So what I recommend is, if you want this page, I will upload these notes later, like I've been doing. But you can just take a screenshot of this. I wouldn't try to like rapidly try to jot this all down because it's like too much. But these are things that we should have sort of be vaguely familiar with from Calculus 1, and we're going to have to use them from time to time. So that time is now. We're going to do another example of integrating that might use one of these derivative rules. Okay. So let's go ahead and integrate. Let's see, problem 8. Let's go with, this is just find tangent x dx. Okay. Now, it would really be nice if we had some integration rules for these trig functions, but like up to this point, we don't. We just have these derivative rules. But if you vaguely remember, if we had this integral, then like if we were to integrate both sides, we could get an integration rule for tangent. But like these guys don't just have a tangent by themselves, so that's going to be a little bit trickier than we need to just have like a go-to like prepackaged function to use. So instead, what we're going to do is rewrite that tangent using an identity, right? Tangent is equal to what? It's sine x over cosine x dx. So just remember that identity from pre-cal, that tangent x is equal to sine x over cosine x. Okay. And then once we have that, we can do that trick where we're just splitting off the numerator and the denominator into 1 over cosine x times sine x dx, right? Because we're kind of setting ourselves up now to use that u substitution that we saw before, okay? So that u substitution says, let's go ahead and set this denominator thing equal to u. And from our calculus rules here, du of cosine should be equal to negative sine, right? Negative sine of x dx. But we don't have a negative sine x dx here. So you could do the same trick that we've been doing. If we had a constant here, we would divide that over. You could just divide both sides by -1 and say that negative du or -1 du is equal to sine x dx. So again, treat these u substitution little statements over here as little equations that you can manipulate as you see fit. But we're just trying to like, fit a peg into a circular hole, right? So we're just manipulating that until it fits this guy over here because that's going to be negative du, right? Okay, and then that guy is u. So once we set that up, we can think about the entire integral is going to be negative because we're multiplying this negative there. So that's going to be a negative integral of 1 over u du. Okay. And then applying that natural logarithm rule, we have negative natural log of the absolute value of u plus c. We're just going to plug that u back in, which was cosine x. Okay. And that's it. So that u substitution is getting us a long way, right? Things that look complicated, if we can find, that derivative in the integral problem that we're working, as long as we label u correctly and then that derivative ends up popping out also in the integral, then that's going to help us like sort of get through that integral problem. Okay. But also, that's what's really nice about this is that gives us our first integration rule for a trig function, right? So now we have this rule that the integral of tangent x dx is equal to the negative natural log of cosine x plus c. So I don't know. Sometimes I like to be silly. A new rule just dropped. Beep, 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 boom. Right? DJ, air horns. Okay. Okay. Sometimes we have to laugh to keep from crying. That's what I always say. Questions about this one? Does that seem okay? All right. It's gonna take a little bit of some work on y'all's end, but that's what college is all about. And then the textbook says, "Hey guys, here are all those integration rules for the trig functions now, so that you don't have to like figure them out on your own." Okay. So again, I ran out of space when I was writing them down. I got a little bit over ambitious, thinking I could write these long ass integrals down. But we have the integral of sine now, the integral of cosine, the integral of tangent, the integral of cotangent, secant, and cosecant. Okay, it's just that these bad boys down here get pretty long, right? And that should make sense because like tangent, if you rewrite it as sine over cosine, becomes one of these like natural log type integrals. So you're going to get a natural log in there, right? Cotangent is also cosine over sine, right? So you're going to get a natural log because we have like a quotient, right? A fraction in that integral if you were to do it by hand, if you wanted to figure it out. But like you don't have to reinvent the wheel. It's been done for you. So as long as you look up these in the ebook or just Google what are the integrals of trig functions, it'll pull up these rules and now we can just apply the rules, right? If we can match the pattern, we can apply that pattern. Okay. So let's look at example 10 to see how that might work. And this is going to be a definite integral, our first definite integral of the day. Hopefully we have enough space here to write it down. Should I start on a new page? These can be pretty long, right? I'll start on a new page. We're approaching the end, guys, so the end is near. Always makes me happy to know that. Okay. We're going to integrate from 0 to pi over 4. Don't you love the pre-cal coming back into play? The square root of 1 plus tangent squared x dx. If I said the phrase to you guys, Pythagorean identity, do you guys remember what that Pythagorean identity is for trig functions? Okay, that's fair. Okay. An answer is always better than no answer, right? So back in the days of pre-cal, you had these identities. Once you see it, it's going to make more sense. And this is why like learning the vocabulary and knowing what these things are called becomes really helpful. You guys remember sine squared x plus cosine squared x equals 1? Maybe not. Okay, maybe some of us remember that. But this identity is basically just a revved up form of the Pythagorean uh the Pythagorean theorem a squared plus b squared equals c squared. Okay. But like with this Pythagorean identity, you can find identities for all the other trig functions. So like I don't have all of the trig function identities memorized, but this one is one to know. Because like if we wanted to manipulate this to get like a tangent, right? Like a tangent squared. Um, what we could do is how will we get a tangent squared? Divide everything by cosine squared, right? Because what is tangent? Sine over cosine? You guys okay with that? So I'm going to try to turn this guy into a tangent squared by dividing it by cosine squared x. And if I divide that by one term, then everything needs to be divided by cosine squared x. So this guy over here becomes our tangent squared x. Cosine squared x divided by cosine squared x is what? Just 1. And then, do you guys remember what 1 over cosine is? There are little tricks that I remember, but 1 over cosine should be secant. Okay, so that means 1 over cosine squared is secant squared. So that's going to be secant squared x. Okay. But now, we don't actually, we have what we need, right? Because we have a 1 plus a tangent squared x here. And we have a 1 plus a tangent squared x. It might not be in the same order, but that's this thing that's inside of the square root, right? So now using that Pythagorean identity, this guy is just equal to secant squared x. So this can be switched over to the square root of secant squared x dx. Integration limits stay the same. And then if you take the square root of something squared, that'll cancel out. So we have 0 pi over 4, and that's just going to be secant x dx. Okay. Okay, so this is, I'm just going to put a little note here that this above was just pre-cal stuff. And man, I think the thing that makes Calculus 2 and Calculus 1 so difficult is that we're asking of you to remember all of this stuff from algebra, all this stuff from pre-cal, or at least have like those fact sheets ready to go, right? Like if you go to physical math world, we have those fact sheets already printed out. So if you're working on a problem and it's like, hey, this person needs a unit circle, let's grab that unit circle. Because like who has time to remember where exactly all of those angles are? If you need a pre-cal trig identity, let's go ahead and grab that sheet because like who has time to memorize the entire zoo of trig identities? There were far too many of them, right? So it's really just about do you know where the tool is? And then do you know how to use it once you have it, right? Okay, so don't judge yourself too harshly if you don't remember these identities. Just the identities that you use over and over again, like the Pythagorean identity, that's a real simple one, can make a bunch of the other identities. Okay, but again, those are the kinds of things, the tips and tricks of the tray that you'll get in math world. We just need to integrate this secant x, right, dx. But we gave you that now, right? And I think actually, did we not do a secant x before? What was the last problem? It was a tangent. Okay. We don't want to reinvent the wheel. We can go back to this that says secant u du is just going to be equal to the natural log of secant u plus tangent u plus c. Okay. I'll leave that on the board for a second, just so you guys can see it. And I need to sort of commit this to memory while I flip the page and hopefully I remember everything. Right. So secant and then tangent. Okay, so then this is just going to be, I've already forgotten it. It's the natural log of secant x plus tangent x plus c. But we're not doing plus c here because we're actually doing a definite integral. Right, let me just double check. Natural log of this plus that in the absolute value plus c. But we're not doing an indefinite integral, so we can actually evaluate this from 0 to pi over 4. And we're going to really just let the calculator do that heavy lifting for us. So equals the natural log of secant pi over 4 plus tangent pi over 4 minus the natural log absolute value of secant of 0 plus tangent of 0. And let me go ahead and write that down so you guys can see it. You guys ready? I always like to take care of this subtraction one first, so I'm just going to kind of work this backwards. Secant is 1 over cosine. Okay, so I'm going to put cosine 0 in my denominator. So this is going to be a 1 there. Okay, tangent of 0 is 0. So that's going to be 1 plus 0 inside the natural log, right? But the natural log of 1 is itself equal to 0. Okay. So this term over here becomes negligible. All you really care about is that term in the front, the natural log of secant pi over 4 plus tangent pi over 4. Okay. So if I put secant, which is 1 over cosine of pi over 4 in the calculator, it's going to give me a decimal number, right? And I think as far as we're concerned, I don't think that an exact number is going to be manageable here. This ends up being the square root of 2, right? And you could go back to uh, the unit circle to sort of evaluate that and get the exact value. So that ends up being the square root of 2, okay? I'm not going to pull out a unit circle here and sort of torture you with that. I'm going to call that the square root of 2. Plus tangent of pi over 4 is 1. Okay. And remember, this other natural log that we had over here ended up being the natural log of 1, which was 0, and that's why we're just ignoring it. Okay, it dropped out. All we have is this left over. Okay. And in some places in WebAssign now, they're going to say, go ahead and round off to 3 decimal places. So like, let's just put that in the calculator. We've already done enough work as it is. I'm going to put the square root of 2 here, plus 1 inside the natural log, and I'm getting about 0.881, and I'm just rounding off to 3 decimal places. Okay, so just make sure you read those instructions carefully to see how far it wants you to round. Okay. How do you guys feel about that? Kind of a lot. Let me see if I can zoom out here. There we go. But I think like with this video, you should be able to tackle this homework assignment. I am going to just briefly, I know that you guys feel like utterly thrashed, right? How are you guys feeling? You guys with me? You guys exhausted? Yeah. It's early morning on a Wednesday, and ain't nobody got time for all this calculus shit, right? Okay, but that's fine. We have one more problem to do from section 5.8 just to set you guys up for success. Okay. Integrals of trig functions. So this section starts off by giving you the keys to the Ferrari, right? And your job is to not crash the Ferrari, right? We don't have to reinvent the wheel. They just gave us these integration rules. So let's just look at one example, and I'll leave it to you guys to sort of get in the homework and practice applying these rules. Okay. And then we'll call it a day because I can see the exhaustion on your face. I can smell it. Okay. I can smell the fumes. All right. Do you guys want some time to write that down or? Okay, I'll give you guys a moment. Write that down. Okay. When you're looking at a problem like this, we want to just match that pattern with one of these inverse trig functions. And so like 1 over something minus something inside of a square root, which inverse integral does that look like? Number one, right? The one that resulted in an arc sine, right? So I'm going to write that down. We're looking at the integral of 1 over the square root of a squared minus, and then the x is the function of u, so that's going to be u squared dx, and that's going to turn into your arc sine. Okay. Arc sine of, what do we have? U over a? U over a plus c, is that it? Yeah. Okay. So then the next thing you have to do is like, okay, let's say if this is our a, well, it has to be a squared, right? So if a squared is equal to 4, then what is a equal to? Yeah, a is equal to 2, right? So we want to do that rewriting. A little bit of u substitution and a little bit of a substitution now, apparently. So we'll rewrite this as 1 over the square root of 2 squared, right? Minus, and then now we know u is going to have to be equal to x, right? For the same reason that, this was x squared, so maybe I'll write it in the same format. If x squared is equal to u squared, then that means that x is equal to u. Okay, so we'll put that, and I like to put in parentheses x squared there, and then we'll write our dx on the side. Okay, so we have our a and our u. So if we have that set up, no need to do u substitution here. We have the keys to the Ferrari, so this is going to just be arc sine, right? U over a, so that's going to be x over 2, and that's it, plus c. Okay. So I know that maybe it doesn't seem like enough examples to get through this section, but actually this section of homework 5.8 in WebAssign, I think probably only has 8 to 10 questions, so it's a little bit trimmed down. And you're just going to be applying as best you can these integration rules for these inverse trig functions. Okay, so just at the risk of exhausting you guys by giving you even one more problem, we're going to call it there. Okay, so let me go ahead and stop the recording.